Hello everyone. Welcome to this session on functional programming. We will be covering the basics of it using TypeScript programming language. You really need not be an expert in TypeScript to understand the concepts presented, but a preliminary knowledge of JavaScript is highly desirable. I will explain some of the syntaxes of TypeScript on the go, but you don't need to really know it in detail. All right. Okay. Without further delay, let's begin. So what are we going to cover today? We will be covering these topics: pure functions, impure functions, how JavaScript supports functions as first class, what do we mean by higher order functions, closure mechanism, currying and partial application, and then imperative and declarative styles of programming. And then we will conclude with our observations, and also we'll look into some of the references into which we can go in deep. Okay, so let's begin with the pure functions. Before we begin this is a Jupyter notebook environment, and thanks to a runtime, JavaScript runtime called as Deno, they have a support for JavaScript and TypeScript for Jupyter notebook. You can directly use JavaScript or TypeScript. Usually, Jupyter notebooks are quite famous in the Python community, but thanks to Deno, you can now use TypeScript as well. And this helps you to put together the nodes as well as your code together in one place. So it avoids context switches between your slides and code. So for that reason, I'm using this. All right. You don't need to know anything about it, but for those who are curious about this environment, I just mentioned it. Okay, let's begin with pure functions. Let's start looking at some of these simple functions. There is an add function. If you look at it, I think you can guess what it does. It takes two arguments, which are numbers, and returns a number. This is how you supply types in TypeScript. You put a colon after your parameter and then supply the types like this, right? So, and after this function's arguments, you can put a colon and specify the return type as well, like just like this. Okay, so here you actually take two numbers and compute the sum of them and return it. And these are all assertions. Okay, so I'm using an assertion library that is also provided by Deno. You have asserts libraries available in Node as well, or any other programming language. You will have some sort of assert library that helps you to write tests, right? So this is kind of mechanism to test your code. So here there are three tests. So basically you are trying to add 3 and 5, you should get 8, minus 1 and 1. If you add, you should get 0. And if you add 0 with itself, you should get 0. So these are 3 test cases I have here, right? So you can run. And assertions have a property: when all invariants pass, right? All these conditions pass, they hold good, they run silently. Assert will run just silently. But should there be a problem, for example, the implementation is wrong, right? So if it is subtracting rather than doing an addition, and if you are trying to say add 3 plus 3 and 5 should become 8, this will not be the case. In this case, what will happen? Assertion will come back and cry foul at you, right? So it is going to scream at you, saying that, hey, the actual value I'm receiving is 2, minus 2, but you are expecting 8, right? So this is a very nice handy tool to give you a feedback. Should you do some refactoring of your function and should it break? These tests can act like guards, right? So that is the beauty of it. Let's fix this and again run it. Now the assertions will all go silent again, right? So there's no problem. So everything is running fine, right? Cool. So we will be using assertions here and there to test our functions. Of course, we might use console log also if you want to see the output, real output for any reason. Okay, cool. So this is add function. There is this 2 Fahrenheit. It will take a Celsius value and convert it into a Fahrenheit. Again, there are tests. These tests run just fine. There is another function called as trim, which is going to take string as its argument and is going to remove trailing and leading spaces. All right. Don't worry about this logic. Of course, you need to loop through, remove all those spaces which appear at the beginning and the end of the string and return the trimmed string. Again, there are some tests, all right? So here we have a test where there are leading and trailing spaces in the string, you should get a string which has those spaces removed at the beginning and at the end, but the intermittent spaces should be retained, isn't it? So there are tests, and this also should just work fine, this test case, right? So great, yeah, it also runs fine. So these three functions, there is fourth one called as add entry, and here there is a type called as record, okay? So this is a TypeScript type. It's actually saying object is a key value pair. It's a dictionary basically. In TypeScript, they call it as record, and key can be value of type string, and the value must be a string. What are we doing here? We are adding a key value pair to this object or to this dictionary. Okay. So how do we do that? We actually create a shallow copy of the object, and we simply check whether this key already exists. If it already exists, we don't want to disturb. If it doesn't exist, we are going to add this key and value pair to that object. And here there are some simple tests, right? So object one is containing these two keys. We are adding a key called a C with value cherry. The moment we add, our expectation is that the result one should become this. If we add a key which already exists, it shouldn't affect, right? So we are trying to add a key which already exists, so it doesn't add it. So the result to 2 should be exactly as the original object, isn't it? So that is what is happening here. And then, yeah. And then it should not affect the original object, isn't it? The object 1, it shouldn't affect. It should retain whatever value it had intact. No modifications should be visible. Similarly, if I add a key value pair to an empty object, you should get those values added to that object. So simple test cases, I think it's all evident. There is a beauty in these functions. What are the observations? None of these functions read or write a global variable. Neither of them write something to console. They do not change their input arguments, right? So for example, here add entry. This object was not modified directly. You always used to get a new object, isn't it, as a return value? The original object was intact. Here there is a test, for example, isn't it? No mutation of the original object. The original object should be intact. Even though you had added some key value pairs, you get a copy of the object rather than the same object getting modified. They are not doing any network calls, no file IO, no random number based computations. Also, they do not throw any exceptions. So these are all the properties of a pure function, and all these 4 functions have that property. And whenever you see these functions, you can always see the outputs can be mapped to their inputs. So output computation is purely based on the inputs that you supply. So that means that if you repeat the same function call with the same input arguments, you should always get the same output. It should not differ, right? Look at that. We have actually ran these tests twice, and in both cases, the result should remain the same. So these are pure functions. Again, this concept has nothing to do with JavaScript. This concept remains the same even if you use Python or C++, whichever other programming language. The definition remains the same. Now, when there are heroes, there need to be some villains as well. Let's look at them. Okay? Impure functions. So by just looking at this function increment and log, you would see it is doing a lot of things which pure functions will never do. Here it is modifying a global variable. It is also doing some IO. It is writing it to console, isn't it? And also it returns the same global. So now I can test this, right? So here I can test increment and log. And to understand the behavior, I should know the implementation details of this function and see what and all side effects it has, right? So it is incrementing this global counter. Because of that, now global counter must be 1, right? In this context. Great. But now what I can do is the same assertion, I can make it to fail by just uncommenting this line, right? So the moment I uncomment this line, the assertion is going to fail, isn't it? Because I am now changing this global. And since this method depends on that global, its behavior is going to change. So there are some external factors also here which define the behavior of this function, isn't it? And in turn, whenever this function runs, there will be some side effects. Some global variable is getting changed here, right? For example. Okay. Now, similarly, there is a function called as array by adding, right? So there is an array and you are trying to add an array. What it is doing is, it is simply pushing the item into the input array and returning that array. Because of this, what is happening here? I have an array. I invoke the array with invoke the function with this array as an argument with the value which I want to add, right? And I seem to get 1, 2, 3, which is right. But if I invoke the same function again, what is going to happen, right? Do I get 1, 2, 3? Let's give it a shot. Give it a try. Obviously not, isn't it? The second assertion fails as you expected because it is modifying the argument itself, right? So as we know in JavaScript, primitives are passed by value semantics, whereas objects and arrays are passed by reference, right? So if I pass an array, it is the same array in the memory, even the function also makes use of, right? So because of that, if I say array.push, what is going to happen? The input argument itself, its value is going to change, isn't it? You are having that side effect here. The moment you execute this line, now nums array is no longer to be containing just 1, 2. It is also going to contain 1, 2, 3. Because of that, this second assertion is going to fail. And this value is actually now has become 1, 2, 3, 3, isn't it? Because every time you invoke this, it is modifying the argument. And since this argument type array is passed by reference semantics, you end up modifying the same array, right? So this is another side effect here. You are modifying the argument. So argument is differing every time you run this, isn't it? And it's very difficult to test these functions. You need to know what side effects they are causing, right? And for those who are curious, what are these symbols between angle brackets, right? Less than, greater than brackets. So this is generics. So basically what we are telling to TypeScript is, hey, the type of these arguments will be decided by the values you supply to it, right? TypeScript can infer. So if I hover over this, right, so the type is getting supplied as number because TypeScript is inferring the type from this nums array. It knows nums is number. So you are trying to add numbers, an item to numbers array. For example, I cannot do something like this. It is not going to allow you, right? So this is actually an error, right? So of course, right now we are not seeing that error here. But ideally, you should see an error, right? It should not allow you to add a string to this array. This is Jupyter notebook environment. You can still see that it's not getting caught. But ideally, this should not be the case. You shouldn't be able to add a string to an array of numbers, right? It should be flagged here, but it's not happening for some reason. But that's okay, right? So, but in a proper TypeScript environment, this should be flagged as an array. Okay. Cool. Let's try that again. I think it is showing that as an error. No, it's not flagging it as an error. That's fine. Okay, so this is generics. So here, you know, right? So array and the value that you are trying to push should be of the same type, right? And you are going to get an array of the same type as well. It's an array of numbers. But since it is modifying the input argument, this function is an impure function, okay? So let me run this again. Values, of course, this is failing because there is a side effect. So now this assertion is going to pass. So these are all impure functions. So what are the key characteristics of impure functions? They tend to modify globals, or they might perform some IO operation or write something to console, for example, or they might be mutating input arguments, which we just saw, or they might also rely on some external factors like current time or random number generation to perform their computation. If it depends on such things, right? So the behavior of the function will differ every time you execute it. You cannot predict what it is going to generate, isn't it? So these are impure functions. We should note that testing impure functions is very difficult because they will have side effects. So we should have less and less number of impure functions in our application so that our application is more testable, right? Our functions are testable and thereby application becomes more robust. Okay, so we discussed pure and impure functions now. Let's see how JavaScript supports functions as first class. What do we mean by that? So we should be able to treat functions just like any other primitive variables like numbers or strings, okay? So you should be able to assign them to another variables. You should be able to pass them as arguments to some other functions, or you should be also able to return them from another function. That means that you should be able to nest a function within another function as well, right? So let's look at some of those examples. For example, here we have a function, right? And we have omitted the name. Such functions are known as anonymous functions. Here we are using function keyword to create functions in JavaScript. And we are assigning it to a string. And that variable can be yet assigned to yet another variable. And using that variable, we should be able to invoke it, isn't it? We are able to do that, right? So here functions are getting treated as any other values. And there is another way in JavaScript to introduce functions called as arrow notation or something called as lambda expressions that comes from the mathematical foundations of functional programming. So such functions are known as lambda functions. So, and we call them as arrow functions because we use this arrow to separate your, signature of the function and the body of the function. And if the body of the function contains only single line or expression, you can omit these open braces and an explicit return statement. You can completely avoid this, right? You don't need to add this. This is redundant in the case of arrow functions, but in the case of function keyword, you have to specify this open brace and close brace with this return statement. But with arrow functions, you can omit, provided you have only one single line statement in it, right? Only in that case, if it is a single line expression, then only you can you can omit those. Otherwise, you need that. So this is arrow notation. There are some other differences between functions created using function keyword and arrow functions. I will not talk about it right now. It is not needed for our today's discussion. Okay. So, but other than that, they are similar. Okay. It's one and the same. Both are doing the same thing. So you can run these functions and they must do do the intended behavior. It's the same behavior, isn't it? All right. Similarly, here we have add one function expressed as arrow notation. Using arrow notation, we have created the function. Just we are repeating it, right? There's nothing special here. Instead of one argument, now you are taking two arguments. This is how you specify the function signature, and this is the body. Again, a single line we have as a body of the function. We are avoiding the open brace and close brace and the return statement. All right, cool. So now let's look at another example for each element. So a function applies a callback to each element of the array. What is the callback? This argument, right, is a function actually. Again, this function is a generic function. You have an array and you have a callback, right? And this function doesn't return anything, but it actually calls this callback on each item of the array. So what are we doing here? We have an array of numbers. Okay, before that, let's look at the logic. What is it doing? Basically, it has a loop and it loops through every item in this array and it calls the callback, right? With that value, right, at each index. So those many times you end up invoking this callback pass to it. That's it, it does. See here, callback, we are calling it as just as a function because it is a function, right? Functions are first class. So because of that, you can pass them as arguments. Now what happens? We'll use this for each element. What are we doing here? We have a callback. What that callback does, it simply pushes whatever items it receives into an array called as collected. Of course, this is an impure function, isn't it? Just for testing purpose, we are doing this here. And then we call this for each element numbers. and the callback. And now you can guess what it will do, isn't it? It would have added or pushed all those elements in the original array into collected array. Collected array was empty earlier. After we call this for each element, it should contain this. Before this, it should be empty, isn't it? So it should be an empty array. So you can add an assertion for that also, like this. Before I call this, it should be an empty array like that. But after I call for each element, it should contain these, right? These values from the original array. You can also simply invoke it with the, let's say you want to log every item in the array. You can do it like this. So let's run it. Assertions are passing and this line here, right? So this is actually printing those items to the console, right? So you are passing a callback as an argument to another function. So passing a function as an argument to another function. In that case, we saw here. Let's move on. We have a function called as give me a function. Now, what is it doing? It's actually creating a function within another function and returning it also, right? If this is difficult to understand, you can say const some function is equal to this, and you can also return. It is one and the same, okay? Since we don't do anything else, basically what we have done, we have created a function within a function and we are returning it as our value. This function is returning a function as its value. You can see here, it takes a string as an argument, but returns a function that also takes an argument of type string, but doesn't do it, return anything. So the return type is mentioned as void, right? Cool. So since we don't do anything here additionally, we are just returning this function. You can short circuit it like this. Earlier we had that, right? So you can simply say return like this. Simply create that function and just return it. This is also the short version of the same thing, right? And there are some assertions. Now what happens if I say give me a function and pass hello to it? What do I get? I get a function. Look at the TypeScript's type inferencing. It says a function that you get is a function which can also potentially accept a string and does nothing. It doesn't return anything. So what I can do now? Sorry, it returns, isn't it? Actually, this is wrong. It actually returns a string, isn't it? Right? Let's fix that type here, right? So now a function is going to receive a string and is finally going to return a string. Sorry about that, right? So this function does return a string, isn't it? So to make the type specification right, I can put this string. These are all getting inferred by TypeScript. So even if you miss it, that's perfectly fine. TypeScript can very well infer it. Okay. Cool. So now I get that function. I can invoke that function. I know that function also receives another argument world. And when I run this, the final string will be hello world. Right. It looks like a magic. We'll discuss about this magic in a while. But this is how you can actually return a function from another function. Let's look at another example, symbol factory. It also takes an argument, but returns a function that doesn't take any argument, neither it returns any value. And we are using some of the JavaScript's inbuilt functions, set interval and set timeout. Set interval can actually invoke a passed in function every second in this case, or whatever time interval that you want. And set timeout is like a normal timer. It will go off after set amount of time, right? And invoke that function and go off. Here, set interval is calling a function called as display symbols. How do we get that function? We actually invoke symbol factory function. And by virtue of calling it, we know that it is returning another function. Okay, we capture it in this variable because functions can be assigned just like any other values, right? To a variable. We are doing that. And we are supplying that as an argument to this function, set interval, right? This is an inbuilt function which can take another function as its argument. So is set timeout. It also is taking a function. We can actually supply the function definition directly as an argument as using this arrow syntax, right? Or you can even define it using function style also, right? So we have used arrow. We prefer arrow notation as much as possible compared to function, but you can use intermittently, interchangeably, you can use either notation. Cool. So let's see. Let's have some fun. Laughing cats, right? So let's run this. Wow. One more laughing cat appears every time. All right. So basically, we are running it for 4 times. After fourth interval, this is going to clear that interval, isn't it? After that, it just stops. Otherwise, you can see these cats appearing indefinitely, which we don't want to happen. Anyway, the purpose of these exercises is to see that a function can be passed as an argument and a function can be returned as a return value. That's what we wanted to convey here. Great, isn't it? So then let's summarize our observation, right? But before we summarize our observations as something called as higher order functions, let's look at a few more examples. Create multiplier, right? This is returning another function. Create greeter, it takes an argument and again returns another function, right? Again, the same thing we are looking at, right? So use cases where you are returning functions as return values. And there is one more example called as create counter. We are seeing more examples to cement our knowledge. That's it. Here also you have this function create counter. Create counter returns another function and you can invoke it. So what are these? So let's run them to see whether they are working as expected. So here we are saying create multiplier. We get a function called as multiply by 2. And when we say multiply by 2 and pass 5, we are getting 10, right? Some magic again. How does this magic work altogether? Because we observe that this multiply by 2 is remembering this argument 2, which was passed when it was created. How does this all work? We'll see it in a while. Now, right now, don't worry. Just accept this magic. This also works. Create greeter. It takes a greeting, right? A salutation as its argument. And say hello remembers this hello. And say hello also in turn takes another argument here. Look at that, right? So say hello Bob. If I supply, as you expect, it will display the greeting that was hello and then the Bob. In the case of say hi, it is this hi it displays first and then Charlie. If I run, it just works like that. Create counter, what it does. This function has access to this variable in its containing scope. So whenever you say create counter, counter 1 would have remembered this count. And when you actually invoke them, you will see this behavior. The first time it is run, it is going to give you output as 1, right? So you can run that and see at 1, and next time when you execute counter 1, you get 2. You have counter 2, again invocation of create counter, you have a fresh function for you. This time this counter 2, right? Again, that also maintains its reference to that variable count, which was present in its containing scope, and it works like this. Cool. We will see how does this work, right? What enables this functionality in a while. But all these functions are higher order. So let's define higher order functions now. A function that takes one or more arguments which are functions, or it might return a function as its return value, or both. It can take as well as return, right? A function as its return value. So such functions are higher order functions. All the functions which we just saw, for example, for each element or create greeter or create counter, right? Or multiply, create multiplier, all these functions are higher order functions by this definition. So I think higher order functions, this concept is clear for all of us, right? Super. Now, we saw a lot of magic, right? Those intermittent functions and them remembering those arguments which were passed to their creator functions, etc. What is that mechanism, right? That mechanism is closure. A closure is the combination of function bundled together with the references to its surrounding state or lexical context or lexical environment. In other words, a closure gives you access to an outer function's scope from an inner function. In JavaScript, closures are created every time a function is created, a function at function creation time. Whenever you create a new function, there is a closure, okay? So that enables this behavior. For example, in this case, create greeter, right? We invoked the create greeter and we passed hello. Now we have a function, isn't it? We know when I invoke create greeter with a value, I'm going to get a function, say hello. Now, when I execute say hello, we also know that say hello also takes another argument, isn't it? So when we do that invocation, Bob, say hello still remembers this greeting, isn't it? So this execution happens only when I invoke this say hello, this inner function, isn't it? But still it remembers this greeting. And this mechanism of remembering, right, all the variables in the containing scope or context is known as closure, right? Because of that closure mechanism, whenever that function creates, that closure under the hood is getting created to mean it has all the references to the variables which were introduced when its containing function was invoked, right? It could be the arguments or it could be the local variables in this containing context. So that closure gets created and this inner function remembers all those variables. Okay, it has a link to those variables. It can read those variables. It can write into those variables, right? In the case of greeting, it was reading. In the case of counter, right, the inner function was actually modifying the variable in its context. So this mechanism is closure mechanism. Hope that is clear. Super. Now let's look at something called as currying and partial application, right? So this is interesting. What is that? Currying is the process of transforming a function that takes multiple arguments into a sequence of functions, each taking a single argument, and the innermost actually implementing the final logic using the closed over parameters. Currying enabled us to create intermediate functions such as add 5, and 10. We have already seen that, right? So here, for example, okay, we haven't seen. Let's see that. Okay, I think we fast forwarded a bit. No worries. Let's come back. So we had this function add 3 here. We have this here, which takes 3 arguments, A, B, and C. It is returning the sum of it, right? At the same time, now we know this higher order function. We can actually create a similar function in here, which has the same behavior, but at every step, what it is doing is taking only one argument and it is returning us a function, right? That is going to take the next argument. And that also is going to return us another function. And finally, the last function is going to receive the last argument, right? And it's going to perform the needed operation. So the process of converting a normal function into such a sequence of functions, right, is known as currying, right? So add 3 was taking 3 arguments. Because of that, we have here a hierarchy of 3 functions, right, nested within each other. The moment you invoke the outermost function, you are going to get the next level of the function. And again, when you invoke that with the next argument, you are going to get the next function in sequence. And the final function is the one which actually takes the final argument and is going to perform the final operation. So the process of converting a normal function into such a sequence of functions is known as currying. I'm just repeating it. And because of this currying now, we have a side effect, okay? I can say add 3 numbers and I can pass just 5 and I can get another function, right? 5. And the beauty of this function is that it remembers this parameter, this argument which was already supplied, right? Add 5. Now, if I say add 5, 10, this is supplying the next argument, isn't it? It is going to get you the final function and that you can invoke with the final value. And such, applications, right, where we are partially supplying the arguments. We are not supplying all the arguments that are needed to perform the final operation, but we are supplying few of them and we are getting these intermittent functions, right? And these intermittent functions can take the rest of the arguments and finally you have the final function, right? These applications, partially supplying these arguments and creating intermittent functions is known as partial applications. So this is a partial application, this is a partial application. And out of these partial applications, you get some intermittent functions, right? And you can run that, right? The final function, right? I mean, final result here, you can see it should behave just fine, right? It should get the 35. for example, here. Or you can invoke the same function, curried function. You supply this argument, you get a function. Again, you supply the next argument, you again get another function, and you can also invoke that function, right? And you should get, in this case, value 6. Just works fine. This is currying and partial application. The immediate benefit of currying is you can do partial application, right? And using partial application, you can create these intermittent reusable functions. For example, now you get this, right, add 5. And you can use this add 5 as many number of times. You can call this add 5, and you can pass 10, for example, you to create add 5 and 10. You can create add 10, add 15, add 100, whatever you want, right? You can create those functions just like that. For example, if I want another instance like const add 10, I can do that, isn't it? Add 10. This should be simply add 3 numbers. Instead of 5, I need to pass 10, right? See, this is a function add 10. Now it remembers this 10. Now I can actually invoke. I can do something like this. Assert equals. I can invoke add 10, and then I can supply 5, and then I can supply, let's say, 2. So what do you think the output will be? 10 plus 5 plus 2. 17, isn't it? Yeah. Now if I run this, all assertions should just work fine, right? So this way you can create these intermittent functions. Right? You don't need to use any function keyword, no arrow functions involved here. You can simply execute this, right? Functions to get those intermittent functions. That is known as partial functions, right? So when you do that, what happens is that you get these intermittent functions. Let's look at another example. Log function. Usually whenever you write some software, you would have this kind of functions, isn't it? So here it takes module. You also many a times also log the line number. Here I am just omitting that, and then level of the log and the actual message that you want to print. So like this. So here you can call that function. But in, you know what, in a given module, this first argument is almost always fixed. And let's say you always want to log debug messages. Again, this debug also becomes, or warning in this case, it becomes fixed rate, right? So what you can do is to avoid calling log with these two parameters every time, you can invent a nice utility function called as log service and var. But for that, you need to, use function keyword and introduce explicitly a function. You need to create that definition, and you need to hard code this service and warn. And then you can call that like this. But you know what? If you turn this log into a curried version of it, like this, right? First level of the function will receive module, next level will receive the level, and the final one will receive the message. You remember, right? The currying, we just curried the add function. Similarly, we can curry the log function, and we have done this here. And this is a union type TypeScript construct. It is, you can say, hey, level can be only warning or debug or information. It cannot be some other string. Okay, that is the union type. So now we have this curried log. We no longer need to create our own function. We can simply call curried version and service. We can pass this first argument. The moment you invoke this, you get a function. To that, you can pass the next argument to get the final function, isn't it? So this becomes your log service 1.1. You don't need to use function or arrow semantics to create a new function. Instead, you can use this partial application itself to create new functions. And now you can use, just like how you used log service 1, you can use this version of log service 1.1 function and achieve the same thing. If you want log service debug, you can always create that function, right? So this is the beauty of partial applications, and JavaScript is quite powerful. You can create a higher order function called as curry, right? Using that, you can get the curried version. You don't need to manually convert a given function into a curried version of it. You can use curry instead. So look at that, you get the curried add here. I don't expect you to understand this at this point of time. I will leave it as an exercise, right? You need to be a little deeper into the facts as how functions work in JavaScript, right? So what do we mean by um, uh, arcs, for example, right? So here there are so many details. There is some recursion involved, right? So I will not get into the details of this. I will leave it as an exercise. Anyway, the fact is that you can have such a function. Now you can get a read version of it like this, and you can achieve the same thing, right? Wonderful, isn't it? So now the functions created using these partial applications are also known as point-free functions. Okay, so one more fact. All right, so we explored partial applications and currying. What else? Let's dive into now imperative and declarative styles of programming. What do we mean by that? Let's look at some of these functions. Basically, I want to convert this array into an array of squares. How do I do that? I can sit and write this logic, right? Every time I want to do that. Of course, I have created a function for that, but this function is not necessary. Directly, I can write this logic wherever I want. Right, and this works great. If I run this, right, you can see the squared numbers you are getting. Right now I'm just logging, and I have a suffix here, imperative, just to indicate that this whatever I'm doing is an imperative logic. What is this imperative style of coding? Imperative is nothing but we are exactly mentioning how things are done, right? They are final instruction to the computer. They are very closer to the computer, right? So here the instructions are that there needs to be a temporary array. You need to loop through that array, input array, whatever you are receiving, and do whatever transformation that is needed, in this case squaring, and push that result into the temporary array, that is squares array, and finally return it, right? A lot of details here, right? So creating the temporary array, initializing it to an empty array, and then looping through from 0 to until you hit the last item in the array, and performing that transformation to that element at the index I, right? And pushing it to the squares array and returning it. A lot of details. These details are wonderful, right? They are needed to perform the final computation. I'm not saying that imperative coding is not needed. It's wonderful. But what happens is usually, let's say now you want capitalized strings, right? Same operation, you are transforming an array of strings into an array of strings only. But the thing is, each item is getting transformed. For example, if the array is apple, banana, cherry, you get capitalized strings, right? So you get apple, banana, cherry, but where the first letter is capitalized, isn't it? That is what is happening. So if we closely look at both of these, a lot of things that are common, isn't it? Every time we are going with the details, how to do things, right? Can we do better, right? Imperative implementation of transforming an array of numbers or strings above focuses more on how to do things, right? The exact algorithm, right? Can we do better with this, right? And the answer is yes. You can come up with an abstraction called as map. Because in both of these implementation, these things remain the same, right? Creating a temporary array, iterating through each item in the original array, transforming, right, every item, and pushing that transformed value. All this logic remains the same. Only the transform changes, isn't it? In this case, it was capitalizing. In the case of numbers, it was squaring, right? That is the only thing that changes. Now, having said that, what we can do is we can come up with a higher order function called as map. It will take the original array, and then additionally the thing that changes is the transform, isn't it? What do we do now? We will take that as an argument. So every item, how it should be transformed. So that becomes a argument, and since this argument is a function, map becomes a higher order function, isn't it? So again, it uses generics, right? So input type of every item in this input array is of type T, and we can potentially transform into another type also. A number can be transformed into string also, right? There's no restriction, right? What that transform can do potentially. That is why we have a type for that output array, right? U. It can be of type U, right? We say they can be same also in these cases of strings and numbers. Input and output arrays had the same type, but it need not be the case, right? For example, what I can do is, for example, I can think of a transformation. You have an array of strings, but you want to get an array of lengths of those strings. Here, the transformation is from array of strings into array of numbers. Okay, hope you can get that. So now we can use this map tool, right? And that original implementation, those 3 lines, that algorithm thing that we saw is completely removed. Instead, we have this map now, right? I can use this map. Using this map, what I can do, I can supply the numbers and I can simply specify the transformation that I need and I can get the same result. For example, now I can also transform, let squared, not squared, the strings, right? Capitalized is equal to map. And what was the array that we used there? Let's say words, isn't it? Okay. So capitalized, I can use those words as is. All that I have to pass. Now you will receive word here. Its type will be string. And it is going to return me a string only. So how do I do that? Capitalizing, I will copy the same logic. It is this, right? I'll just copy that logic. That is the body of this here. Okay. So instead of words I, it should be word now, isn't it? Word, and this also word. You will have the same result, right? So same assertion now should pass, or same console log should hold good here as well, right? I can bring it here, can put it here, and instead of capitalized imperative, I can now paste this, right? So, and I can run. Now what is happening here, right? So you are getting the capitalized strings, right? Just fine. Looks like there is a problem in my logic. What is that? Word character 0 to uppercase. Oh, oops, it had to be word. My bad, right? Okay, same result you are getting, isn't it? Now look at the beauty of this, right? All that I am doing is calling map, right? Now from how we are transitioning into what? Now the question is what? What is happening here? Map is happening. What do you mean by map? Actually transforming, right? Input into output. So here it is very clear. If I just look at this, it's all evident, right? What is happening? You are actually squaring every item in this array. Here, if you look at this, you are sure that every word is actually getting transformed into capitalized version, right? So instead of these 3 lines now, your focus has shifted into what? This is declarative style. And actually, you know what? You don't have to implement this map function in JavaScript. Array of JavaScript already supports map. So you have it already. So we just implemented it to make the point clear how exactly it does the transforming. But you don't need to implement it. It is already there in the JavaScript. Or even you can invoke it directly like this and you get the necessary transformation happening. Similarly, filtering is also a common problem. You have numbers, for example, you want to filter evens, right? Again, you have a temporary array, you need to loop through it, you need to check a predicate on every item, and you only if that passes, you push that item into your result and you finally return the result, right? Similarly, here there is a function filter long strings, right? Basically, you say you filter all the strings which have minimum length, whatever minimum length you are supplying. For example, here I'm saying that I want to filter all the strings whose length is greater than 4. I can do that. Again, every time we want to do that functionality, we are repeating this logic, the how logic, isn't it? Look at that. We are repeating it. What you can do? Same thing, you can invent a filter function. Input array, you have a predicate. That is what changes, isn't it? Predicate is a function that checks a condition and returns a Boolean, isn't it? And the return value of this filter function will be of the same type, right? Filtering will involve same types. You don't get a totally an array, a result array having some different type, right? So type remains the same. So here we are filtering a numbers array. You should get a numbers array itself. And again, you don't need to implement this filter on your own. JavaScript array already has it. You can invoke that as well, right? Cool. So that is filter. Now there is a third example I want to draw your attention. That is accumulating values in an array, right? Basically summing up, for example. Here you have imperative sum. Basically you want to sum, right, all the values in this array. For example, const initial value is 0. And then you have an accumulated, right, which starts with the initial value. And there is this loop. You iterate through this loop. Every iteration you simply accumulate because your aim is to sum up, isn't it? So you just add that item to the accumulated every iteration and you return the final value. Again, this is an imperative code. Similarly, let's say I want to concatenate all the strings. What I can do, I can start with an initial value. I can have another variable called as accumulated, right? To which I can initialize that initial value. And then I can loop through it. All that I have to do is I have to concatenate that string, right? You'll get the concatenated string like this. This is again imperative logic. What we can do is we can invent a function called as reduce, where this algorithm is captured. What really changes is this reducer function, the way we accumulate at every step, right? That is the thing that changes. Rest everything remains the same. You have an accumulated that has an initial value. You have a loop. Every step you accumulate. That we actually convert it into as an argument, right? It becomes a callback for us. That will receive accumulated value and the current value. And it is supposed to define what does it mean by accumulating, whether it is concatenating or whether it is adding up. It's totally up to the reducer function. Now what we can do is, the moment we have such a function, now we can find the sum like this. We pass this array and the accumulation is very simple for us. We simply have to add, right? Whatever accumulated that we are receiving, simply add the current value to it, right? So it should just work fine. And you know what? Again, JavaScript's standard library already has a reduce method defined on the array. We can use that as well. So simply pass the reducer function and the initial value, you should get the same result as well. That is reduce function. Reduce is a very powerful abstraction. It is also known as fold function in the functional programming world. Okay, now let us look at an imperative implementation where we filter odd numbers and then square them and then add them. This is an imperative logic, right? So we have a sum here. We actually loop through here, right? Every item in the array. We check this predicate whether the number is an even number. Then only we do this transformation, squaring and adding it to sum. This might be a simple one, but it is having a lot of details. How details, isn't it? The how aspect comes into picture here. You need to carefully look into this function and figure out what exactly is happening, right? Of course, this is going to work, right? But you know what? Now we have filter, map, and reduce tools in our hand. What we can do is, instead of inventing such imperative code to perform that, what we can do, we can say, hey, numbers, what you need to do? You need to first filter all the even numbers. And we know that this filter function is going to return us another array. So we can chain these calls now. On that array, I can map, right? I can transform that filtered values into their squares. And then what I can do is I can perform the final operation, that is reduce, isn't it? So that reduce, all that I am doing is summing, isn't it? The current value with the accumulated value. But this solution is the declarative solution. Beautiful it is, isn't it? Because it's all evident now what is happening. And there's less scope for errors now because you don't need to create these kind of temporary variables. You don't need to use these kind of loops and indices. Loops are totally avoided, right? Creating temporary variables are avoided. And you now bring in a lot of meaning to your code, right? So it's all high level now. Now I can, by just looking at this, I can make sense out of this. If I know this filter, map, and reduce, what do they do, right? If I know that, I can very well understand what is happening here out of the box. I don't need to worry about the inner implementation details of it, right? So this style of programming is called as declarative style, right? So of course, there are a lot of things go into it. Here, an array gets transformed into an array. Because of that, we are able to chain these functions, right? Chaining is also a very fundamental core concept of functional programming. We will look into that in maybe separate session altogether. But here we are seeing the tip of iceberg. We have seen this filter, map, and reduce, and because of their existence, we can now come up with this kind of powerful abstractions, isn't it? Now, if I ask you to, let us say, hey, I want you to simply square these numbers and give me only the odd numbers. How can I do that? It's quite simple, isn't it? Okay. Now, const odd squares. All that I will have to do is numbers. First, I need to find the squares. I need to transform, isn't it? Number. What I can do is number into number. Now I got that array of squares. Now what do I need to do? I need to filter only the odd numbers. So I should use filter, isn't it? So again, number. I have to supply the predicate. So if this is, the remainder is not equal to 0, right? That means that will pass, isn't it? So odd numbers will pass this predicate, isn't it? Now you get the odd numbers. So I can actually log them and show it to you. Odd squares, right? Look at that. Again, this becomes a declarative way. Declarative in the sense, by just looking at the code, you know what exactly is happening. No implementation details are thrown at your face, right? So you know these constructs, what do they do? And because of how they also compose with each other, how this chaining works, you can intuitively figure out, isn't it? Let's run this. You should get the squares which are odd, isn't it? Quite powerful. This combination is so powerful that you can solve a lot of complex problems, right? Especially dealing with array collection, right? And the reduce is quite powerful. You can express almost any other function using that. For example, you can express map using reduce. All that you have to do is your reducer function, right? This is your reducer function, right? All that it has to do is every step here, it should accumulate the transformed function into the accumulated array. And the initial value of that array will be empty. Every step, it simply accumulates the transformed value. So finally, you will get what you will get? The transformed array. So it's quite powerful. Now I will leave it as an exercise for you to implement filter function using reduce. I will leave it as an exercise. Wow, we have come along so long, right? Long way we have traded. Let's conclude our observations. So in nutshell, functional programming involves pure functions, more pure functions. We have to eliminate side effects. We should avoid mutating states or mutate, for example, mutating arguments or globals, right? And we can actually invent partially applied functions using currying mechanism. And that enabled us creating point-free functions, reusable functions wherever we want, which would remember the closed-door context. And then finally, we also looked into what do we mean by higher order functions, and then this imperative and declarative styles. And in the process, we learned map, reduce, and filter functions, and abstracting out business agnostic reusable higher order functions, basically. Yeah, again, they were map, filter, and reduce to enable declarative algorithms. So these practices collectively form the foundations of functional programming. There is much more to this. For example, composing of the functions, piping, and concepts like functors, applicatives, monads, and whatnot, right? But those concepts we will touch in our future sessions. But for today, only this much. Okay, before we sign off, let's take a look at some of the references which I have found quite useful. JavaScript, the Good Parts by Douglas Crockford is a must read for any JavaScript developer. He discusses the core strengths of JavaScript, including its functional capabilities. And functional programming in JavaScript by Luis Atencio is an excellent book which introduces functional programming through JavaScript in a systematic manner. Composing Software by Eric Elliott is also a great book I have found useful. Structure and Interpretation of Computer Programs is a classical literature on computer programming. It introduces a lot of programming techniques, including functional programming techniques. And original book was written in Scheme, a dialect of Lisp. Now there is a JavaScript version as well, so you can go and check it out. Along with that, I have a quiz app which is hosted, so you can click on this link and see test your knowledge. All the material is available in this repositories in GitHub. The link is provided in the description below, including the Jupyter notebook and the quiz app and this references list. Everything is available there. That's it for today. We'll meet in another session. Bye for now. Thank you so much.